past units, and I've always just kind of said, it means add it up. So just don't pay attention too much and just add the stuff up. But let's actually hone in now and like pay attention to the really minute details of this notation. So it's called summation notation or sigma notation. This is a capital sigma. You've seen obviously recently the lowercase sigma. The lowercase sigma is the one we use for standard deviation, right? So this is a capital sigma, sigma for sum, right? If you were Greek, you'd be like, of course that's the letter we should use. But to you, it's like, why do we use an E? But it's an S. I mean, it's a sigma, capital sigma.
Sigma for sum, not that for others.
K, we use K as the index variable, or whatever letter you like over here, right? The thing that goes here, like you see down here and here, is always the explicit rule, never the recursive rule, always the explicit rule for some sequence. Here, down below, we have the lowest index and the highest index you want to consider, and you step from the low index to the high index, stepping by 1 always. You plug in all of those things into your explicit rule and add them up, right? So, for example, down here, that's a period. This is a sentence, and that's the period. Sorry.
That's so awkward.
It's how you do it. Sorry. It's correct. I don't know what else to say. It's not a mistake. All right. Yeah.
If it's sigma for sum, what is it for others?
Okay, Ian, calm down. I heard you the first time. I just chose to ignore you. Okay. All right. K, guys, we have a lot to do here. Okay, K equals 1 to 6. So what does that mean? It means let K be 1 and 2 and 3 and 4 and 5 and 6. Plug those into this explicit formula, which is pretty simple here. This is pretty exciting, right?
Yeah.
Okay, you want to just like text your friends and stuff about it. Are you tweeting this out? What are you doing?
Live took Mr. Chase's lesson.
Right, I know. So plug those in and then add them up, right? So plug in 1, plug in 2, tell me what you get for each of these, and then add all those things up. Do the same down here, right? Start with 4, go to 7, plug them all in, add them up, and in a second we'll solicit answers from my 2 favorite strings. Yeah, start with the lowest one and go to the highest number, right? Stepping by 1, plug them each in. So when you're ready, how about... Yeah, the first one. Are you more confident? Did you do it already?
Why did you throw that? Tell him to stop throwing pencils. Shine's throwing pencils.
How's it coming?
I was thinking about something else.
5 is what you're plugging in.
Yeah, that was what I was thinking.
Yeah. You are an expert. Check these 2 answers.
Oh, you got it out.
Did you get that for the first one? Yes? Did you get that for the first one?
Why is the number on the... Daisy, can you add all of them? Why is the letter N on the top? On the other side, like
On the side? Yeah, whether it's displayed or in the middle of a paragraph. I want you to know how to do both. All right. If there are no discrepancies, we're moving on. All right, things you can do with the notation you've just been given include, notice you could have done this to make your work quicker on part A, for example. It should be pretty clear why this works too. It's basically just us using the distributive law, right? On what this says is on the previous one, on A, we could have done instead 2 plus 1 plus 2 plus 3 plus 4 plus 5 instead, right? 2 times all that. Do you see how that's still the same thing on part A of the last one? That might have quickened your work if you had noticed that you could do that, since you're doing 2 times 1 plus 2 times 2 plus 2 times 3. This just says, yes, in fact, you're right. You do have permission to factor something out of the sum. If that makes your life easy, do it. This property says, again, just from basic principles of algebra, says that you can break apart the sum, right, into 2 separate pieces. So if you were adding up, if you were doing this, you could sum each of these. You could sum each of these individually instead, right? Can we kill some of the side conversations? Thanks. Bring it to 0. Thank you, guys. Just so people can think. All right. So I think that makes sense again, too. If you write out the terms algebraically, you have like all the terms from k squared next to the terms from 2k, but there's no reason they had to appear in that order. You could have all the terms from k squared followed by all the terms from 2k. You see that that's just a rearrangement that takes advantage of the commutative and associative laws. This last one's kind of crazy looking. I would call it like the re-indexing rule. So for this last one here, for example, let's show you that on part B of the last slide, we could re-index that. It was k squared, right? Running from k equal, or what was it, k? N something, whatever. Re-index it. Let's have it start from 1. Some of you are like, why does it start with 4? I don't like that. Well, you can change it. Let's have it start with 1 instead. Now the answer still needs to be 126, right? It still needs to be the same sum. I do not want to change the sum. I still want to do whatever rewrite I have. I still want to have be equal to the original one. What this says, though, fix that, okay. What this says, though, is if we take the bottom limit, which was 4, and we make that go down to 1, then we still need to have the same number of terms, don't we? So what does the top limit need to be then? Instead of 7, it needs to be what? If this one went from 4 down to 1, yeah, they both need to go down by 3 then, right? But if you do that, then the rule here can't be k squared anymore, can it? Because then you'd be doing 1 squared plus 2 squared up to 4 squared, which is not, of course, what we want. So what do we need to have the rule be here? We still want to have us be adding. Yeah, we need to like add 3 inside here. And then notice that all we've done is something cosmetic. The moment you start actually valuing the sum, plug in 1. Go ahead. Plug in 2. Go ahead. Aren't you getting the exact same thing you did on B in the last one? Isn't it 4? Oh, yeah, 4 squared plus 5 squared plus, and then 4, plugging 4 in, that'll be 7 squared. So yeah, that gives you the same thing.
Why
So,
would you want to do that?
I don't know, just for fun.
But doesn't it have like
Yeah, there are. One thing that's maybe not obvious when it is true, a lot of times I think you maybe do prefer having 1 as the bottom limit. So if someone wants you to have it be 0, and you want to be like, I don't really like that, I'd like you to start at 1 instead. There are lots of places in math where we may want to like re-express our sum in a way that's like more familiar to us. So I think you're right to be like, it's weird that we went from 4 to 7. That is a little weird, I agree, okay? So one thing this is not like the reason you have to do this, but one thing that's not super obvious right away on this, how many terms is this?
5, 4.
Right? It would be very clear, look up here, this is clearly 6, right? So here's one kind of silly reason. It's because, one reason you might like 1 as the bottom limit is because then the upper limit is the number of terms that we have. Why is this 4? I don't know. What's the rule? How do you do this? I don't know. So what do? You subtract them, but then you have to like add 1? Yeah, just like when I assign homework problems like 4 through 7. How many homework problems have I assigned? 4. When your English teacher asks you to read page 30 to 40. You have 11 pages to read tonight, right? All right. So let's try homework 2. Let's try these properties out. You always do.
Did you seriously say that everything came out?
There you go. I'm covered forever. There we go.
What is it?
You have to find what homework of one.
Well, I assume you did the homework last night. So whatever it was last night. There you go. I just don't feel like updating it ever again. There you go. Powered math. Okay. So this equals. You guys got to simmer down. Sorry. Okay. So this equals this by one of the properties. Yeah? We said that that was true. You could break apart the sum. Now, we don't even know what these rules are, by the way. This is some explicit rule. Maybe it's like, who knows, n cubed minus n or something, right? And this one is the square root of n. It could be some crazy rules. Who knows? But it doesn't. If we're given the actual result of these two sums, then I think we can handle this problem, right? Yeah, we can factor this out using one of the other properties. And now we have the things that we're given, right? By the way, feel free to add to all the sigmas, the limits of our sum. So these are given, right? 2 times -2 minus 5 times 5 equals something. It's given in the problem. All right, let's take a volunteer on this first one down below, whenever you're ready. Again, the point here on these is, can you just re-express the sum so that 5 is the lower limit? That's all, right? When you're ready. Or over here, so that -2 is the lower limit. Anybody want it?
I can tell you what n is.
Sure.
30.
Good. What do you have to do here?
Subtract 5.
Yeah. So what do we have to put here? Go ahead, Alexis.
No, I don't think I can. Wait, hold on. Where are you subtracting the 5 from the whole thing?
Yeah, from the 2 plus 5.
Keep in mind that even though we don't know what this sum is, it's terrible, right? 26 terms, right? We can still write another sum that has as its sum the same sum, right? And the way you can verify that is make sure that whatever you say down here for the rule, that when you plug 0 into here, you get the same thing as if you plug 5 into here. Now what would assure that that happens? Yeah, well, I don't know. What makes sense to you?
Okay, so you subtract it from each page. You already said yes.
Do you see why though? Because in some sense you want before this function ever sees the k, you want it like to turn the k into a 0, and now it's a 5, right? Like you want like a filter on the front of this that turns 5s into 0s. So yeah, I think every k needs to have instead a k minus 5, right? And then that will make sure this is the same. So what do we have up top? Just k? What do we have down below? What would that be? 2 to the k minus 5 factorial. Just verify that if you plug 0 into this, just feel it. Plugging 0 into this is of course the same as plugging 5 into this. If you want to check the end condition too, try plugging 25 in here or 30 in here. Doesn't it feel the same? All right, now I want a volunteer to take this. Sophie, I'm going to come over there and take that phone forever. Put it away. Don't incur my wrath. Thank you. Who wants this one? You gonna let Ian take it? No, don't do that. He's so. Yeah, there we go. Good. Go ahead, Cass. That looks like a very exciting series, doesn't it? So she subtracted 2 from both of these guys and added 2 to all of these guys.
Why do you do that?
Try it and just see, right? If you put in -2, don't you get 5 here? Just like when you plug 0 in, here you get 5. It's just that adjustment, that's all.
Wait.
Huh? We gotta make you masters of series. Yeah. No. Keep trying. I'm glad you're looking. Not very many people have
I need while you wait.
Yeah, you should play around with it. It's such a simple looking problem. It's really hard. Alright, so consider that, let's actually see if we can derive a rule for the arithmetic sum. So, yeah, we gotta do both. Yeah, 'cause you guys keep interrupting me. Ah, let's go. Okay. Alright, we gotta move, guys. Okay. It would be nice, especially in light of the fact that like when we were doing those sums, it was like hard enough with just a few terms. What if we asked you to do, and I think we have lots of reasons to want to do this. What if we wanted to add up a whole number of terms of an arithmetic series? Well, I think it would look like this, right? Can we come up with a formula for this? Thanks for stopping the talking, you guys. I've color-coded them. This is term 1, A1. This is in blue term 2, isn't it? A1 plus 1 copy of D. In purple, that's the third term, isn't it? I'm just doing this very, very generally. And as we talked about the other day, this is the nth term, isn't it? If this is really an arithmetic series. I'm rewriting the series down below backwards. This should say n. That's an n. So do you agree that this is the backwards version of the same? This should be the same sum. The last term followed by the second to last term. Do you agree that that's the second to last term? It's just the last term minus d. That's all. All the way down to, this is a little strange way to write the first term, but this is the first term. It's the last term minus n minus 1 copies of d, right? Because that's how you got to the last term, isn't it? By adding d, n minus 1 copies of d. So the last term minus n minus 1 copies of d gets you back to the first term. So if you can trust me on that, then I think we're ready to do the following. We're going to add the following two together. And in all cases, as you add colors, what do you get? What do you get when you add all colors? When you A1 plus N, A1 plus AN, A1 plus AN for all the colors. We also on the left get what? On the left, 2S. So how many colors are there? How many? There are N colors, right? Because there are N terms. So there's a quick way to write that. That's just N times A1 plus AN divided by 2 gives, in a box, our result for an arithmetic series. So, so quickly check for the sum that Fatma did, right? You did this one. That was arithmetic. 2 plus 4 plus 6 plus 8 plus 10 plus 12. That was arithmetic. What was the first term? 2. What was the last term? 12 divided by 2. And how many terms was that? 6. Does that come out to 42 for her series that you did in A back on the last slide a couple slides ago? Does that come out to 42? Try it.
Yeah.
Good. So that's not a proof, but it does. Well, this was the proof. But that does seem like it's working. It does seem like it makes sense. That's a pretty slick way to get that. for an arithmetic series at least, we have a tool now to sum those. Sorry, that moved too quickly. You're like, I didn't write anything down, I just wanted the formula. So you said. What about the learning, though? What about the sense making? Okay. Let's give you a sum formula for a geometric series as well. I think you would agree this isn't like the general form, just like on the last slide. But this time the general form for the sum of the first n terms of some generic geometric series. Do you agree? This is definitely the first term. This is in red, definitely the second term. And down here, this is definitely the nth term, isn't it? That's the rule we love. A1 times r is n. This time we're going to use a little bit of a different trick. You can see the trick we did last time isn't really going to work here necessarily. We're going to take advantage of the fact that like there are some multiplicative properties here rather than additive properties. We're going to multiply through by r every term of the whole thing. So here we have rs, of course. Here we have a1 times r. Here we have, instead of a1r, we have a1r squared, etc. All the way down to here, where instead of a1r to the n minus 1, we have a1r to the n instead, right? So all the powers of r just go up by 1. Okay. Now, there's a reason I've color-coded it in a certain way here, because what am I going to do this time? I'm going to combine them somehow, right? What am I going to do? I'm not going to multiply them because multiplying this by this doesn't seem desirable in terms of like the number of terms that happen.
Add, divide, subtract.
One of those. If you add them together, what will you get? You'll get this plus this. I'd love something to go away again, right? You guys are worthless. Okay, all right. Subtracting, obviously. I didn't mean that. I meant every one of you is dying. Sorry, I'm running out. Too little sleep. S on the left we have S minus RS. On the right, everything goes away except for A1, and then we're subtracting this. The only thing we're subtracting that remains is A1 minus A1 R to the n. Factoring out an S on the left and an A1 on the right, and then dividing by 1 minus R gives the result. There you go, in a box for a geometric sum. Do you follow the logic here? All the way to here, to the box? I might have to have you prove this sometime.
Well, I'm gonna choke.
Notice that on both of these two formulas, there is a different demand for things that are required. On the arithmetic sum formula, let me say one or two more things here. On the arithmetic sum formula, what was required? We need the first and the last terms and the number of terms. So notice that if I give you some generic arithmetic series, that the first thing you might need to do if you don't have it already is obtain those things. Like you might not know the 20th term, right? So you might need to calculate it first to use the formula. Likewise here, here you need the first term, the R value, and the number of terms. But maybe there's one of those things you don't know. Right? So just be aware that like sometimes we need to do a little work on the front of one of these problems. I obviously would have liked to have done one more slide with an example of these on it, but I think you'll be okay. Just use the formulas. And make sure that you understand where you're going. And I love you all.
That's a lie. You said we were